For the speech. Now we are inviting him via online. Now we have you connected.
Very good. All right. How are you feeling today?
I'm feeling very good. Thank you very much.
We thank you very much. Now, are you ready? Well, we all have very high expectations for your keynote speech today. All right.
Thank you, everyone, for having me to this keynote speech. It is an honor and pleasure to present in this conference. And I understand that Busan is going to be one of the main city for driving Metaverse globally. So let me get started with my talk. First of all, like I said again, thank you very much. And I actually head up the AI technology centers for NVIDIA. So I want to give a quick understanding on give a bit of context on where we are going. First of all, we do know that we are seeing a lot of climate change. One of the things is that the world is getting warmer and warmer, and needless to say, we are very concerned about it. We are simulating whether the world is raising from 1 degree, 2 degrees, or all the way to 4 degrees, which may be catastrophic to the planet Earth. And this actually caused a lot of concern. Things will be like rising of water levels and so forth. Country that is or city that's near the sea will be highly affected by such catastrophe. The other things that IPCC has reported was that there is going to be we're going to see more places going to be warmer, drier, and also wetter. Places like for example, like in Singapore itself, which is the country that I was born in, is going to have a lot of rains, and it's going to be more floods and so forth. And recently, just a couple of years ago, Thailand has a big flood because of climate change. Now, this is going to have a lot of catastrophic events, things like wildfire, more snows, and more extreme weather. And when I say more extreme weather, this is basically that we are going to see more of this. The weather is going to be more extreme, and we're going to see more of this extreme weather. Now, so what are we going to do about this? One of the ways that we are going to do is that we're going to reduce the amount of carbon dioxide that is going onto the planet Earth, or the greenhouse gases. And in order for us to understand how all this thing is going to affect the climate change, we need to find some way of modeling it, simulating it, and so forth. So what we want to do is to look for an old idea. And when I say an old idea, basically the idea come many years ago. If you guys could remember the Apollo program, where we sent men to the moon and then return them to planet Earth, that was the whole mission. Of course, the mission itself create a lot of new technology, but the idea is pretty straightforward. Fire the rocket, bring the men to the moon, lands the lunar modules on the moon itself, collect the samples, and then bring them back to Earth. So the mission was rather simple. The whole thing is that the Apollo 11 is the first one where we have men landing on the moon, and of course follow on with Apollo 12. But what is significant happened on Apollo 13. Now, Apollo 13, as you could see over here, this is on your right-hand side. You see that rather on your left-hand side, you see that the damage of the service module. Now, this is basically what happens to Apollo 13. Now, for those of you who have remember the Apollo 13, is that while it was on the way to the moon itself, the oxygen tank actually got exploded. And it causes two things. One of them is that it ran out of oxygen. The other thing is that it actually of course, it ran out of oxygen, which means that there is not enough oxygen, or rather limited amount of oxygen for the astronaut. The other thing is because the fuel cell, which is the energy we run on fuel cell, require oxygen. It's mix of oxygen and hydrogen to produce the energy. So we have a big problem over here. If, how to actually get the man back onto planet Earth. The mission decided that they should have continue on the spacecraft, go around the moon and fly them back. Remember that this is a few days mission. It is a very long time. So the man is going to have to stay in the spacecraft, go around the moon and come back to planet Earth. Of course, they are not landing on the moon itself. They're going to use the moon as a slingshot to go around the moon. So you have two things. You have to conserve your amount of oxygen. You have to conserve your energy. So what they have done, and by the way, this has never happened before, and they didn't plan for it. So what are they going to do about it? How are they going to go about doing this thing? The lucky thing is that they have a digital twins, or what we call at the point in time was more of an analog twins. They have the duplication of the particular spacecraft on planet Earth. And what they have done was that they bring along all the engineers and scientists to come together to brainstorm, to come up with a right protocol. What are the computer to turn on? What are the computer to shut down? What is how, when, and how the navigation system is going to be powered up? When are they going to fire the thrusters and so forth? So of course, if you guys have followed the story or even watched the movie, you will seen how the entire sequence is all about. But the more important thing is that the engineers and the scientists able to get together in a very short time using the analog twins to simulate and come up with the right procedure to bring the spacecraft back. So the mission right now is a success in terms it's not landing man on the moon. A landing man on the moon is a failure, but the success of having to rescue the man in the middle of a mission, right? Using twins, a computer twins, analog twins or digital twins to bring them back. So with that, nowadays, digital twins or the industry metaverse is heavily used in many industries, whether you use it in aircraft, use it in space, in the automotive industry. These are heavily being used. So let us switch back to the modeling of the planet Earth itself. When we want to model the Earth, there's a lot of challenge. One of them is that the climate itself is very chaotic. Many of you would, and myself would always complain that why is that the weather prediction is never accurate. It's supposed to rain today, but it didn't rain or whatsoever. It's very chaotic. Honestly, it's one of the most difficult to actually model. The other thing is that it has incomplete observation. To observe, to get the data for the simulation, you need a lot of data, but the data are not complete. The other time, of course, a short time to solution. Basically, we want to able to predict in a very short time. And the other thing is that we have finite resources. There is never enough compute data resources for us to predict accurately. So how do we go about doing that? Now, just to give you about the resources that we have, Korea has one of the biggest supercomputer. You have KISTI, right? And there are even larger supercomputer around the world, such as Summit, Frontiers, and whatsoever. And at the moment now, the state-of-the-art system, in order for us to simulate a resolution of 1 kilometers, basically is the current largest supercomputers to do it right now. In order for us to do a 100-meter resolution, we need to have about 10,000 times the compute power that we have. And in order for us to go to 1 meter, we need almost 100 billion, which is basically technically impossible to do that. So what we want to do, and just to give you a context, this is Singapore, and this is a little red dot in Singapore, and this is the resolution that we can do right now. It's a 1 kilometer resolution. which means that it's very difficult to actually use a global model to actually predict Singapore. We need to use a local model to predict Singapore weather. So we have this resource problem. Then how do we go about doing it? So one of the ways that we are thinking of is to make things more challenging is that climate science there is new science coming up, new complexity, new physics, new chemistries, and so forth adding to it. And that makes it even more complex as we get into higher fidelity. So one of the things is that we want to adopt how to use deep learning or machine learning to do the particular modeling to build the digital twins for the planet Earth. So before we go into that, one of the challenges in building a digital twins is that there is a couple of challenges that we need to address. One of them is that, like I said before, in order to have high fidelity, we need to have a very accurate model. We need to have a two-way of synchronizations. The other things is that interoperability. Now, the industry use of various software, there are a lot of software going around and so forth. So how do we get the software to actually interoperate? How do we actually get to share data and stuff like this? The other things is that there is a lack of common standards and tools. So we have to be
네, 그래서 이 문제를 해결하려고 노력하고 있습니다.
Right. So the other thing is that because of the disparate data integrations, we need to have different data all coming into one single location. So these are some of the challenges. And then the last but not least is to establish a workflow. How do we then able to connect all the different mechanisms, tools, and so forth, and put them in a single, very coherent workflow? So let me take a look at some of these. Is that how do we then simulate the physics of whether is it in industry metaverse or a climate science metaverse? First of all, we need to be able to simulate physics in a very realistic manner, right? Things will be like, and there are a lot of work being done within NVIDIA using physics X for the gaming industry and into the omniverse. The simulating the environment itself, things like, the climate, how the spacecraft or aircraft is coming into atmosphere, the fluid dynamics, all these things, we need to actually able to simulate them pretty accurately. So to simulate the environment, we need a very complex equation. And this, again, don't worry about the complex equation itself, but what it means is that in order for us to have high fidelity, we need to have this complex equation, but this complex equation causes one big problem. The big problem is that the computational requirement become extremely high, which means that we have a big problem in building we need a very big system in order for us to simulate that, which we cannot afford if we want to have very high resolution. So we want to turn on the things is that can we find a surrogate model to speed up the existing code? How do we able to represent those physics that we have learned over hundreds of years and put them into a very more simplified model such that we can actually simulate them, but yet we can retain the high fidelity. So we want to approach it and through deep learning, and they are already start approaching, which I'm going to address a little bit more about it a bit later. So there are physics-informed neural network using and other form of deep learning technology. So let us take a look at the state of the art of AI algorithms right now. First of all, we know that the AI algorithm now has become pervasive. Korea is one of the country where users deep learning in a lot of many things. It's one of the most advanced country in using such. There are a lot of predictive AI. When I say predictive AI, it means that you use to predict things. things like people countings, things like using medical images to detect brain cancers, tumors, or whatsoever. Do facial recognitions, pattern recognitions, and so forth. And this has been progressing very well. In fact, the technology is mature enough right now to actually get implemented. The technology has progressed tremendously. Over the last few years, all this technology has now surpassed human. But by the way, these technology are very narrow. They are not generalized. They are very good at predicting certain things for certain verticals, a certain application. So they are very accurate and they are very good, but they cannot use to predict other things. They can use for predict for examples like facial recognition. They cannot be used for other purposes. So they are very good for one thing, but they are not good to be generalized. But what is exciting over the last thing is that there's a huge explosion of generative AI. By the way, generative AI idea came about in 2014, where we have the variation auto encoders, and then follow on by gangs and so forth. Now, NVIDIA has been doing a lot of things into these things. One of them is that we're using gangs to generate, examples like this to generate artificial face and so forth. We also been using it to generate out things like, sceneries and so forth like this. This is important because this is allow us to start building Metaverse in a very quick way. As you guys would know, building the content within Metaverse is sometimes can be challenging. It is not just the idea of using it, but creating those scenarios is changing. So if we have tools like this, that would be very helpful. Recently, the sudden explosion of diffusion has accelerated a lot of different applications. Stable diffusion itself, of course, is one of them, and it has created a lot of new applications and so forth that allow us to be very creative and innovative and stuff like this. Now, the diffusion method is not something that is new. It's been around for a while. The whole idea is rather simple. It's allowed ones to put in noise, and then in each step itself, and then in the reverse order, we actually learn how to remove the noise and learn about the function. So the whole idea is that, of course, the mathematics and the implementation itself can be complex to get any form of stabilities and convergence. But the ideas is pretty simple. So that give birth to things like mid-journeys. Things will be like stuff like this. A lot of new applications coming out from the diffusion algorithms. NVIDIA itself has also works on things like high resolution synthesis of latent diffusion that we allowed to use making use of LLM together with diffusion that allow us to type in prompts to generate out videos. So that means that now we can actually do a lot of very interesting things. Just by typing in text like this, then you were able to generate out a very interesting video. So this is at the moment right now, this is still in the very early stage. As you could see, these are very short prompts. And there are people already working on making much longer prompts, which means that you can now generate on a much longer video. In fact, the hope was to be able to generate end-to-end, maybe a 1-hour videos using prompts. There are also other things like drag gang from Google's, and also, of course, needless to say, Photoshop itself now implement AI that allow us to do a lot of things. This actually allow marketing peoples in the marketing industries, peoples that doing content creation and so forth to actually accelerate the pace of their work. So you could see that there are all these new tools and all coming up tremendously. Now, one of the things is that if you guys have been wanted, especially for those who are doing AR, VR, one of the challenging things is to create 3D images using 2D photos. And one of the things that NVIDIA are doing is that we have done what we call the instant nerf. And this is just an example of it. So we can create the 3D images in a very short time, and we are continuing on to improve, and hopefully we can do that almost in real time, right? Now, some of you may have watched those technology has created a whole new industry. Some of you may have recently watched these new videos created by Coca-Cola using generative AI. So let me just show you this. Due to the lack of time, I'm going to cut short the video, but you can actually watch it over in many places like YouTube and so forth. So one of the things that NVIDIA is partnering with some of the biggest marketing company to create tools for them using generative AI. And just let me show you the video.
Are racing to realize the benefits of AI. NVIDIA and WPP are building a groundbreaking, generative AI-enabled content engine to enable the next evolution of the $700 billion digital advertising industry. Built on NVIDIA AI and Omniverse, this engine gives brands the ability to build and deploy product-accurate and brand-compliant content faster and more efficiently than ever before. The process starts by building a physically accurate digital twin of a product using Omniverse Cloud, which connects product design data from industry-standard tools. Then, WPP artists create customized and diverse virtual sets using a combination of digitized environments and generative AI tools by organizations such as Adobe and Getty Images, trained on fully licensed data using NVIDIA Picasso, ensuring that generative AI content remains accurate and on-brand. This unique combination of generative AI and manufacturing data allows WPP to build accurate photorealistic visual content and e-commerce experiences that bring new levels of realism and scale to the industry.
So we switch a little bit over to NLP, which is one of the biggest, most talked about technology at the moment right now. Now, many of you will have hear about a lot about ChatGPTs and so forth, and it has caused a sensation. But the natural language processing has been around for a long time, and is born out basically from a transformer, attention-based algorithms that has spawned off to many different type of algorithms, as you could see over in the graph over here. Now, this actually, because of that, the ChatGPT right now is one of the most talked about subject on this planet Earth. There is a lot of debates going on whether ChatGPT has any kind of sentience or intelligence and whatsoever. And many people has done a lot of different tests or whatsoever. Some of these show that ChatGPT are more intelligent than human in doing certain tests and so forth. But in all, from my perspective, ChatGPT or GPT 3.5 and even ChatGPT 4.4 is a conglomerate of, or rather algorithms that take on all the different type of data together and put them into a single place, and then using some kind of probabilistic model which allow it to actually predict the next words or the next sentence and so forth. But because of its high dimensionality of the data that it has, it can do a lot of very interesting things. Now, this allows us to do a lot of things, right? For conventional AI, for example, like in video conferencing, call centers, and retail assistant, and so forth. This is going to change the industry tremendously. And we could see that there is a lot of new application coming out from the development of this. This is a snapshot of the different type of application that is relying on things like the GPT 3.5 or GPT 4. There are so many applications right now that it's almost impossible for me to actually put them in one single screen. In fact, every time I put on a screen like this, is obsolete because there's always new application always coming up. But what I want to show to you is there's something that is very interesting for us is in the engineering and the the scientific computing, and in the software programming space. This is a application that uses the LLM to generate out codes and also to generate out graph. Now we could actually writing codes just using natural language processing. What does it mean is that now more and more people do not need to actually learn complex programming languages. Of course, the programming languages like C, C++ are still needed because they have certain structure and you can actually optimize them. But it democratized the way that we can write programming. Common people who has very limited programming experience of languages, they can now write computer program using common languages. They can now build graph, relationship databases, and so forth, just by using natural language processing. Now, so these are only the early stage on how this technology can be used. The other things that we see is that people are using this ChatGPT for doing many other things. One of them is in the medical space. We have been working a lot with the medical folks itself, and this is examples from a company called Class AI, where you could actually ask the applications about a medical diagnosis, and then they come up with a clinical plan and so forth. Of course, still this is not going to replace a doctor, but it helps the doctors to actually come up with ideas and come up with a solution very, very quickly. The other thing is music, and this is the Google's classic music LM. So now we can produce almost, well, I wouldn't say produce almost everything, but we can produce a lot of things using generative AI. And basically because of the new technology, things will be like the LLM and so forth. And many of you would have hear about people criticizing that the LLM, like the ChatGPT, has hallucination. There are effort that's being done that is things like the self-reflecting LLM agent that actually correct itself. So this is one of the things that people are working on. And there are things like where Hugging Face, where is a Hugging GPT, where they have created these things as an agent that's able to actually access other tools to help them in doing the work. So what this thing is done is that they uses the LLM to actually generate out tasks, and these tasks basically use our task planning, and then they could then select the models, and then do the task execution, and finally they get a response and so forth. So the model itself now becomes like a task agent where they can decide, they could plan out the things and then select the right models, for the optimum models to actually do the right task for whatever request is needed. So these are one of them. And of course, many of you will have heard about the Auto GPT, which is, again, this is going to be a major breakthrough that is basically a GPT agent itself. They're able to self-select, self-learn, and so forth. That's able to do a lot of very, very interesting tasks and so forth. Now, I'm going to delve on it too much, but many of you will have known about this. Let me just, but because of all these things, as you could see that there is a diffusion models and the transformer models that allow us to do a lot of very interesting and wonderful things right now. What is concerning is that all these models require quite a huge amount of resources, because they are actually very large models, consists of billions of parameters, and some of them all the way to a trillion. So some of these, at the moment right now, some of the researchers, including NVIDIA itself, are looking at creating ways of pre-train the models, creating new methods of reducing the amount of computation that is needed for to develop some of these new applications. So let me just switch topics quickly, and how this application apply into science, into climate science itself. So there are a lot of work that's going on right now in the climate community. Things like we use it for some of these applications which I mentioned about, used to accelerate physics parameterizations, and then to and also to do medium weather forecastings, and so forth. As I mentioned earlier, there are data, there are incomplete data on the planet Earth because of there is not enough sensors on the Earth itself. We are still building more sensors, but there's never enough. So one of the ways is to use generative AI to fill in the missing climate data and so forth. The other things is that we are using it for nowcastings and stuff like this. Now let me just also the other things that that we are doing is to do things to simulate the fluids. So one of the applications, one of the techniques that are being used is to use physics-informed neural networks. The whole idea about physics-informed networks is not to use the data itself, but the physics that is available to us. Yeah, using the equations of the physics, we could then use it as a constraint to the neural network. We could then train the neural network in a very take some time to train the neural network, and then after that we could then use the neural network to quickly simulate the model. So these are things, and let me just show you a very quick videos about how do we use it for simulating the wind tunnel.
Currently exceeds 750 gigawatts and is growing faster than ever, with an additional 650 gigawatts to be added in the next 5 years. For companies like Siemens Gamesa Renewable Energy, optimizing the configuration of each new wind farm is critical for getting the most out of their investment and reducing costs for consumers. When designing a wind farm, it's critical to place each turbine so as to minimize the effects the turbines have on each other due to the wake that they create. Accurately modeling the wake requires high-resolution, high-fidelity simulation data that is specific to that wind farm, such as the geographic location and the terrain. The gold standard for generating this data is the large eddy simulation shown here. But to run just one iteration for a single turbine can take 40 days on a 100-core CPU. And with so many iterations needed to develop an accurate model for a specific site, using CPUs is impractical. Using NVIDIA Modulus and NVIDIA Omniverse, Siemens Gamesa has been able to reduce that 40 days to just 15 minutes, approximately 4,000 times faster. This is accomplished by running the model at a lower resolution, and then, with a PhysicsML model trained using Modulus, to enhance or super resolve the data. And the results are functionally equivalent to having run the model at full resolution. Let's take a look at the same data presented in a way that clearly highlights the coarseness of the low-resolution simulation. Here, they look like pixelated blobs. In the super-resolved flow field, you can see the finer vortex structures. Now that we have the simulation data, we can build an accurate weight model for the site and optimize the placement of each turbine. Thousands of iterations, accelerated by NVIDIA GPUs, are run as part of the optimization to achieve the maximum power output for each farm while minimizing the cost. And the impact is huge. When using NVIDIA Modulus and Omniverse for a typical 1,000 megawatt offshore wind farm, optimization can provide power to supply up to 20,000 additional homes, and to do it at 10% lower cost.
So you hear a lot of words about what the Omniverse is about. And the Omniverse basically is a platform that we have built to actually do all the different integration together. Think of Omniverse as the platform that allow different tools, different databases, and things to actually communicate with one another. Remember the things I mentioned before, the trouble of, or rather the challenges of building digital twins. So in order for them to actually communicate with one another, we actually use the USD as the default communication data format platform for these different tools to communicate with one another. So what the Omniverse allow us to do is that we can do full digital replica. We can also use it for true time connectivities, right? We can have different tools communicate with the IoT devices and so forth. And also that we can do analysis, optimization, things like this we can show you in the earlier videos. We have a single source of truth. We can build all sorts of assets into one single area, and then we can allow it distributed across the world. Basically, you can have scientists that across the world to actually connect into one single platform to do the simulation and to collaborate to build the digital twins for science. So back to the things is that using digital twins, what NVIDIA is working on right now is that we want to build the Earth digital twins using Omniverse. In the middle of it, we have things like the using the modulus, which I talk about using is basically physics-informed neural networks with Fourier neural operators and so forth that replicate the partial differential equations by a surrogate models, which is a neural network. That could help to accelerate the simulation in a very, very quick way. And finally, but not least, is that Omniverse is able to put all this together and allow one to actually do the visualization. So our hope is to able to move up the ladder across in this chart that we are able now to resolve some of this and build a digital Earth to a lower resolution. How do we go about doing this? We are still there's a long way to go. We are still working on this. And let me show you a video where we are that we are doing on right now on the digital Earth, visualizing the digital Earth.
High-resolution weather simulations, as provided by DKRZ's ICON code and vast amounts of observational data, allows us to determine the state of the Earth with unprecedented fidelity. But exploring and working with this data can be a challenge. Technologies like the NVIDIA Omniverse ParaView connector allows scientists to interactively analyze weather and climate data in 3D, to combine information from multiple sources, and to explore what-if scenarios. This takes us ever closer to a realistic, interactive digital twin of the Earth. Let's look at two examples. In August 2019, Hurricane Dorian developed into a massive Category 5 hurricane, causing over $5 billion in damage in the Bahamas and the southeastern US, with sustained winds of 185 miles per hour. Viewing high-resolution simulations like these integrated forecasting system simulations in Omniverse allows scientists to analyze the behavior of storms such as this in detail, interactively, and in full 3D. This not only aids in understanding the physics of weather systems, but also allows inaccuracies in models to be identified and refined. With the Omniverse ParaView connector, visualization modalities of ParaView, like streamlines, become available within Omniverse and can leverage the RTX renderer or be fused with data from other sources. These sources can be static or computed on demand, such as mapping service, surrogate model, or an AI-informed physical model. Here we show AI-based image segmentation of satellite data, which was used to detect flooded areas and to classify land use before and after Dorian hit. The network performing the segmentation can run as a service and be triggered on demand. Once we have interactive access to all this Earth science data, a next step is to play through different scenarios. On-demand evaluation of surrogate models or access to real-time physics engines can help exploring the impact of our actions in this virtual world. With access to real-time physics models as enabled by Omniverse, we can not only explore pre-computed data, but also simulate on the fly. Here, we use real-time fluid dynamics simulation to show the vapor plume emerging from a cooling tower. A user can quickly explore the impact of the plume, depending on the wind conditions or the steam output. Similar models can be used to interactively explore the dispersion of aerosols or contaminants. NVIDIA Omniverse is a powerful platform for massive-scale digital twin simulation. We're excited to see where it takes us next.
So with that, I thank you very much for inviting me to this presentation. Thank you.
We thank you very much. 여러분 큰 박수 부탁드립니다.
Please give him a warm round of applause.
기조 발표였습니다.